Well, hi there, sports fans. Welcome to another exciting edition of Physics 12. Today we're looking at lesson 4.2, which is on translational and rotational equilibrium. And we will define what those mean in just a moment. So first of all, let's just look at the conditions for equilibrium. And what do we mean by that? And first of all, an object with forces acting on it, but that is not moving, is said to be in equilibrium. So in other words, you'll have some forces on it. Obviously, a force of gravity will be one of them, and probably a normal force to keep it in one place. But as long as the object is not moving, then it's said to be in equilibrium. And so here's an example where you have a book that's sitting on top of a desk. You have a force of gravity on it, and you have a normal force that's holding it up. This object is in equilibrium because it's not moving. So the book is in equilibrium, and the net force on it is simply zero. So the force of gravity is equal to the normal force, so the net force on it is zero. And in this situation, because it's not moving, this is what we call translational equilibrium. And so don't get too worried about the terminology. Translational is just another word for saying, is referring to the motion of something. So if it's in translational equilibrium, then it means it's not moving. So the second condition of equilibrium is that there is the net torque on something is zero. So the object then is not spinning, or is not causing to be to put it into rotational motion because of a net torque. So in other words, the net torque on it is zero. It's not going to be rotating. So that's the second condition of equilibrium. So looking at an object, you just look at the forces on it, and you ask yourself, okay, is there a net torque on the object? So here's an example here. Let's move that down a little bit here for now. Here's an example here where the net forces on this ruler will produce a net torque of zero. And so if you look here, based upon the forces that I've got on here, the net forces will not produce a torque on this particular object. So if you look at the center of motion here, and we make that the pivot point, or the axis of rotation, we have a force over on this side, which should be balanced out, well, a force that's producing a torque over here, that will be balanced out by the torque over on this side here, and so effectively the net torque is zero. And once again, if this is our center of rotation, or our axis of rotation, then this force right here will not produce any torque on the object itself. So in this case, actually, we have our net forces are actually zero, because we have 10 newtons in the down direction, and we have 10 newtons in the up direction as well. So our net forces are zero, and our net torque is zero as well. So this object is in both translational and rotational equilibrium. So those are both conditions that are necessary for an object to be in what we call static equilibrium, both rotational equilibrium and translational equilibrium. So the object is in a rotational equilibrium. All right, so when we solve these kinds of problems, there's a number of steps that we want to go through. And so the first thing is to choose an object one at a time, make a free body diagram showing all the forces on the object and where they act on the object. And that of course is your first step. Again, free body diagram. Choose a coordinate system and resolve the forces into components if you need to. You don't always need to, but if the forces are not acting perpendicularly, then you may need to parse them out into their components. And then write equilibrium equations for the forces. And then choose an axis that's perpendicular to the plane of forces, and write the torque equilibrium equation. Now this may seem like quite a mouthful, and may seem rather complicated, but I will break it down and make it a little bit simpler with an example in just a moment. And so then lastly, we need to solve for the unknown, whatever the unknown is being asked for in the particular problem. So we'll look at an example here, and here's sort of a typical kind of example where what we need to do is we need to find the unknown distance x. So we have a situation here where we have a person on one end of the teeter-totter here and somebody else on the other end over here, and as you can see, the masses are different, and so obviously the distances will have to be different if the object is in equilibrium. And so here's where we put the forces on here, as well as the distances, etc. This diagram is a little bit complicated, so I have done another one to simplify this just a little bit. So we're going to solve this problem, and I'll show you how we generally do things and simplify things a little bit, because this is a little bit more complicated than what you want to do. If you notice a couple of things on here, though, the pivot point has been chosen right here. So we do pick a pivot point, and then again we have the forces on here, and I will go into those a little bit more detail in just 1 minute. So we do choose a pivot point. When you make your free body diagram, choose your pivot point, which is indeed what has been done here already. And then now, the one thing that is very convenient is that you can actually make your pivot, your pivot point can be anywhere actually. And so you could make your pivot point over here, or you could make it over here. It just all depends on the situation. And generally speaking, what you will do is you make your pivot point one of your unknowns initially. And that will usually help solve the problem. But we will look at that in further detail later when we look at other types of static equilibrium kinds of problems. So let's just break this one down and make it a little bit simpler. So I've redone the free body diagram here. So as you can see, what I've included on the free body diagram is the forces. So I've got all the forces on here, and there are 4. So the forces from the two people sitting on the seesaw or the teeter-totter. We also have a normal force, which has to hold up the teeter-totter. We also have a mass of the board of the teeter-totter as well. And so we have to account for that one as well. So we'll just call that one mg. Now, we can pick our pivot point. Now, this is the most likely pivot point right here. And because the normal force and the center of mass of the board, which again we make right in the middle here, because they act right at the pivot point, they don't contribute to torque at all. So we don't have to worry about those as far as our torque equation goes. And that's the beauty of being able to pick any pivot point when you're solving these kinds of problems. The other thing, if you notice, I put on here the direction of the clockwise torque and the direction of the counterclockwise torque. So there's our free body diagram plus our pivot point. And now what we want to do is we want to write balanced force equation. And so here's our balanced force equation. Now, sometimes you will need to use your balanced force equation to solve a problem. Sometimes you don't. So it just all depends on the problem. In this case, we don't need this. We can solve this simply with our balanced torque equation. And our balanced torques is just simply going to be the clockwise torques, in this case it's just one, will equal the counterclockwise torques. In this case it's just 1 as well. So what you have to be careful though is know for sure which direction you're looking at. So the clockwise torque is produced from the person that's sitting over here. That's producing a clockwise kind of torque. The counterclockwise torque is from this one over here. So that's producing a torque in this direction here. So make sure you get your clockwise and your counterclockwise in the right direction here. So now we can write our balanced torque equation, which is this, 25gx, which is this one here. That's the clockwise torque. Here's our clockwise torque, and there's our expression for the clockwise torque. Here's our counterclockwise torque, which is from this side over here, and they just simply have to equal each other. So there's our balanced torque equation, and then all we have to do then is to solve for x, which at this point is a simple matter. And again, it simplifies a little bit because the g's will cancel on both sides of the equation. So we just have an equation or an expression for x is just 3 times 2.5 divided by 25, and that just equals 3.0 meters. So we've solved this problem, and we've done it step by step. And so here's your steps right here. Once again, draw your free body diagram, pick a pivot point, and usually make your pivot point one of the unknowns. In this case, it didn't really matter too much, but that will help you in the future when we look at more complicated types of problems. This was a fairly simple one. Second step, write your balanced force equation. Third step, write your balanced torque equation, and then solve for the unknown, whatever that might be. Sometimes you end up having to do a substitution. So you use your balanced force equation and substitute that into your balanced torque equation. But those get a little bit more complicated, and we will look at those at a later time.